It's a lecture on group on ring theory, and this is the first lecture of ring theory. In this lecture, I will define various kind of rings and the example of rings and what is a ring. And before that, I am assuming that you guys are already compared with groups, right? So I am not going to define any group, and this is a ring theory course, so it is obvious that you have learned group theory, that basic group theory, not more than that, because we are not analyzing any rings here. So like as groups, the order of an element, we will not discuss this kind of thing. You just have to remind that definition of groups and how they actually works. Yeah, so this is lectures on first lecture of ring theory, and let me set up the definition. This is ring theory lecture 1, and what is a ring? The first question that immediately should ask, what is a ring? Is a ring. What is a group? First of all, what is a group? Group has group G, group has one algebraic G star with an algebraic structure. It's a group and associated with an operation. This is called a binary operation. This binary operation is from G cross G to G, right? This is for group. So ring, in ring we have two operation, right? So one is addition, one is multiplication. We will define two binary operation, right? So not like the plus is the as usual plus and dot is as usual, but there can be anything. Just for convenience, you can say that this is addition, this is multiplication, right? So what is the definition of a ring? So the definition, a non-empty set a non-empty set R. This is not real number R, okay? This is R. This is denoted as a ring. So R with plus dot. Suppose this is two binary operation is called a ring. Is called a ring. So see here, plus is a operation. Binary operation means that this is R cross R to R, and this is also means R cross R to R. This is not real number R, this is just this R. This is a set with some property, we'll say this is a ring. So the first property the ring says called a ring if so R with respect to the first operation plus is an abelian group. Abelian group, right? You know the definition of abelian group. It's as simple as that. This is an abelian group, and the second property that it should satisfy, R dot is a semi group. R with respect to the second operation, right? This is a semi group, right? This is actually the binary operation plus associative. This is called a semi group. So with R plus would be an abelian group, and R with respect to the second binary operation, this is dot, this dot is this dot, right? Second binary operation is a semi group, and there is one more property, that's dot distributes plus. That means A dot B plus C is actually A dot B plus A dot C for every A comma B comma C inside the ring R. If this three conditions satisfies, then we say that R plus dot is a ring structure. Okay, okay, the definition, I guess it should be clear to, the definition is as simple as that. So it is just an R plus should be an abelian group, R dot is a semi group, and dot distributes plus, that's it. So A dot B plus C is actually A dot B plus A dot C, that's it, right, for every A comma B comma C inside R. So this, if these three properties satisfies, that means not three, there is only dominated, there are six properties, that is, this is binary operation, closure, that is binary operation, closure, associative, identity, inverse, okay, and as well as the commutativity. There is pass 5, there is 5 properties there, but the simple as that there is this and this property. If this satisfies, then we say R plus dot is the ring, right? So what are the examples of ring? The first example, that this is the very obvious example. Examples, first of all, Z plus dot. This is a ring. Is it a ring? So for that, first property said Z plus is an abelian group. Everyone know an abelian group, right? And Z with respect to dot is a binary operation plus associative, of course, because R is associative. Here plus and dot are the usual multiplication and addition. This is associative, as well as this distributive. So this Z plus dot is a ring, right? Is a ring, right? So the second example you should consider, Q plus dot. You just verify this all are rings. Whatever I am writing, because you have to verify that. Okay, so R plus dot is a ring. Example 4, C plus dot is a ring. And fifth example I am in Zm addition modulo m multiplication modulo m is a ring. You have to verify this all are rings. You have to check the properties, these three properties, right? Whether this is abelian, this is semi group, and this is distributive, and this three property, and this property holds. If this three property holds, then we say. So this is Q, right? Don't confuse. What happens here? This is Q, right? This is rational number, right? You have to show this all are rings. Highlight is not working, so anyways, you can, yeah. So this all are, you just have to verify this all are rings. Okay, this is some trivial example, examples of rings, and everyone should check this all gives a ring structure, right? That's it. So let me give some non-trivial examples. Non-trivial examples. Some non-trivial examples. What kind of non-trivial examples? So first, you can take, the power set of natural number with respect to the symmetric difference and the second operation in intersection. This is a ring. Is this a ring? Is it a ring? See here the symmetric difference, see this plus is this and dot is this operation, right? So power set means the set of all subset collection of all subsets of n. Okay, and you have to check the three properties that r plus is that means you have to prove that power set of natural number with respect to symmetric okay, let me define what is symmetric difference. Symmetric difference of a symmetric difference b is actually a union b, a union b minus a intersection c, a union b minus a intersection b. This is called the symmetric difference. Symmetric difference, right? Symmetric difference and asymmetric difference is this. So can you verify that this forms a ring structure? So let me verify the first one by one. So this is one example and verify the properties. Verify property 1. What is the first property? That power set of natural number power set of natural number. What is this happening? Power set of natural number with respect to symmetric difference should be an abelian group. Everyone know this is an abelian group. Why? Where every element is of every non-identity element is of finite order, but this group is not an infinite group. Okay, this is an example of this group. We have seen that power set of natural number with respect to symmetric difference, as every non-identity element is of order 2. That means every element is the inverse of each other. So this is power set of natural number is an abelian group, right? So this is most trivial, or you can verify this is an abelian group. But their identity is empty set. Identity is empty set. Okay, and whatever you will check. So it is very easy to check. So power set of natural number, you just the second property what it says. Okay, let's check the first one, otherwise you will not understand. So how do we, this is an abelian group. So first of all, this is a closed, right? So whatever element you take, a union b minus a intersection, this is also a subset. This will be definitely a subset of natural number, right? So this is the closure property hold. It is closure property holds. Closure holds. It is obvious. This I am not going to obvious. Okay, closure associative. Okay, suppose a b c with two element of power set of natural number. So you have to show a symmetric difference b, a symmetric difference b, symmetric difference c is actually a symmetric difference b, symmetric difference c. See, what is a b symmetric difference b? That is a union b minus a intersection c, a intersection b. This symmetric difference with c, right? First I am looking for this. So this is actually a union b minus a intersection b. If you have to set, and what is this? a union b see here, you can see if you have two set, suppose two are intersection here, suppose this is our intersection here, that is a, this is b, suppose this is c, right? So a union b will be this entire set, a union b, right? minus A intersection B means just this area. A intersection B means this area, just this area, right? So you will just have this area and this area. So but this portion and this portion, right? A union B minus A intersection B. That means you just only the working area. Our working area is this and this, right? And symmetric difference with C. That means this area, this portion. That means the portion that we have, this portion union with C will give us entire area with C, and intersection with C will just this is not an element. Intersection with C, it will remove this area and this area, the entire area. So we are lefting out with this area, and this area, right? And similarly for A, similar, if you let me just, you are only every other here, right? Here, you are here and also here, but not in the intersected area. You can look like that as a Venn diagram. So similar thing if you draw here, right? This is C, this is our A, this is our B. The similar thing I'm writing. So A intersection B symmetric dependency. What is B symmetric dependency? That means B and C, and B intersection C is this, right? This is our B intersection C. B intersection C is this. So B union C will be the area this B union C. So this B symmetric dependency will be the red area, right? The red portion. Then A union B, sorry, B union C minus B intersection. That means this has been removed. So after that, so this area has been taken care of, and after that what you have is it is with A. So this total area with A, that means this total area union A, that means this red area with total A, that means this portion is not included with A, minus this total area minus, that means you have to remove this part and this part. You have to remove this part and this part. So you are actually getting exactly this one, right? See here, this is our not included, this part is our not included, this part is also our not included, and this part is also not included. This is exactly same here. So actually you can verify that A union this is associative. And theoretically you can also prove, right? So you can also definitely also can prove by theoretically this is associative. So what is the identity? What is the identity? What is the identity for them? A symmetric difference, let us suppose E be the identity. This is actually A, suppose it is the identity, this is A. What does it mean that A union E intersection minus A intersection E, this is actually A? What is the possible choice of E? A. This is actually gives us the choice for A union empty set minus A intersection empty set, which is equals to which is actually equals to A, because you take here A union empty set means A minus A intersection empty set means empty. This is empty, which is actually E. So this is, so identity is E, which is empty set. What is the inverse? What about the inverse? Inverse, suppose a b equals to e. B is inverse of a inverse is equals to b. What is the possible choice of b? So e is empty set, so a union b, e, b minus a intersection b is equals to empty. What is the choice for b here? What is the choice for b that such that it will be empty set? So actually it is, you take b to be I guess you take b to be natural number, then you take natural number union a, that it will be a minus, and if you take b to be natural number which is a, yes, you take b to be a union natural number, the entire set, minus a intersection the natural number, which is actually equals to a union natural number, means the entire set is a minus a intersection natural number, means this is a, which is actually empty. What is a possible choice for your b is the entire set n. This will work for every n, so inverse is n. So inverse and associative commutative is, of course, I guess the commutative or abelian. A symmetric difference b is equals to a union b minus a intersection b, and b symmetric difference a is actually b union a minus b intersection a. They are precisely same. There is no difference. This is clear. A union b and b union b is same, and a intersection b and b intersection c, they are precisely same. So this is commutative, right? So this is, so first one, so power set of natural number with respect to symmetric difference is an abelian group, right? Abelian group, right? So you just to say that power set of natural number with respect to intersection, is it a semi group? Is it a semi group? So it is a semi group because it is a binary operation, of course, because you take two elements from power set of natural number, it will definitely be a member of this power set. That means it will definitely be a subset of natural number. This is already member of power set. The associative, of course, this is associative, you just have to prove. So associative is also, and distributive is also, and distributive is also, yeah, distributive is also. So you verify the rest operations, right? So yeah, so power setup, you will see that power setup natural number with respect to symmetric difference and intersection is a ring. No, what happening here? Yeah. Yes, it's a ring. So let me ask one question on this. So this is an, and don't see the answer of this, and I will just pause it and think about it. So first, let r plus dot, why this is be a ring, sorry, not ring, be any abelian group, right? And A dot B equals to 0. 0 means additive identity, right? Additive identity. So for every A comma B inside the ring R, can you, so can R be made as made a ring? This is my question. Let R plus be any ring. My question is R plus be an R plus dot, this is a ring. So you have an operation A dot B equals to 0. That means the additive identity. So can R be made a ring? That means can you give a ring structure on R? If you can, so what will be the operation, what will be the addition, what will be the multiplication, right? So can R be made as a ring? That means you have given, this is an abelian group, right? R plus B given to you an abelian group, and you have two things that you have is A dot B equals to 0 for every element. So this happens for every A comma B, sorry, every A comma B inside R, right? For every A comma B, A dot B equals to 0, and 0 is the additive identity. That means identity with respect to the first operation, with respect to plus, right? Additive identity. Can R be made as a ring? Just think about it. The answer is yes. You can give a ring structure on R. The answer is yes. Yes. How do we construct? So first property, it is abelian. What you have told, you just have an R plus, you have an abelian group, nothing else has been given to you. Sorry for the inconvenience, but my point is not actually, just let me just a second, let me make it more precise. So let R plus be any abelian group, and for every A comma B inside R, A dot B, this is equals to 0, which is additive identity. That means this is 0 is an identity with respect to plus, with additive identity for every, for every I have written. So can R be made a ring? This is my question. Be any abelian group. This kind of question is very trivial question, and this kind of question you might ask in any interview, right? So if you have any abelian group, can you give any abelian group with the operation that A dot B equals to 0 for every A B inside R? So can this R be made as a ring? Answer is yes. You can make. Yes. How? Let me give you, but before giving me, you just think. So first property is it satisfying the first property? R plus is an abelian group, group. This is satisfying, right? What is the second property? A dot B, this is 0, right? A dot B, this is 0 for every A comma B inside R. What does it mean? That dot is a binary operation. Binary operation and associative. As well. What? Because the associativity because comes from A dot B dot C, which is equals to A dot. What is B dot C? B dot C is 0 because for every element A comma B, A dot B is 0. So every B and C, so B dot C is 0 and A dot 0 is 0. This is 0. And what is A dot B dot C? This is actually 0 dot C, which is equals to 0. So this is a binary operation, right? Because 0 is an element of R. So for any element you are operating, this is actually 0. So this is a binary operation as well as associative. This implies that R with respect to dot is a semi group, right? Is a semi group. So semi group plus associative. Associativity comes from here. So this implies R plus dot is a ring. Okay. So there is one more property. Sorry, associativity comes semi group. Semi group means the associativity comes. You just have to verify one more property. You have to verify semi group. Okay, this binary operation plus associative means this is semi group. Anyways, so the third property you have to say. The third property is such that dot distributes plus. Dot distributes plus. So it is quite trivial. It's the same thing whatever I have written. A dot B plus C, and B plus is a member of R. So A dot B plus C will be 0. Which is actually A dot B plus A dot C, right? And A plus B dot C, which is actually 0, which is actually A dot C plus B dot C, right? So dot distributes plus. So this is also happening. So 1 through T3, the three properties are satisfying. This implies R plus dot is a ring. So this is a ring. So my conclusion is every abelian group can be made as a ring. Why this pen is doing this kind of things today? Every abelian group can be made a ring by defining by a suitable multiplication. TION. So every abelian group can be made as a ring by defining a suitable multiplication. If you ask any kind of question, then if you have an abelian group, can you make as a ring? Can you make this as a ring structure? You will say yes, I can give a ring structure on it, and by defining the suitable multiple operation is actually a dot b equals to 0 for every element a comma b inside the ring R. Okay, so every abelian group can be made as a ring. Every abelian group can be made as a ring by a suitable operation, right? Now I am coming to okay, one more thing that I just wanted to say, that this ring with plus dot is called a zero ring. This is called a zero ring, right? This is called a zero ring, trivial ring. So now I am defining commutative ring. Commutative TIV. What is happening? Commutative TIV. See, plus is always commutative, and whatever you will do in ring, you just have to, the commutativity you will check under the second operation, that is dot. So commutative ring, a ring R plus dot is called a commutative ring if a dot b, that means the second binary operation b dot a, for every a comma b inside the ring R. This is called a commutative ring, right? A ring R plus dot is called a commutative if this is commutative with respect to second binary operation. See, the first binary operation is already commutative because the first option, what is it, the R plus will be an abelian group. So there is no, so if then there is no meaning of the abelian commutativity here, but R plus is not a group also, right? So R plus is just a semi group, that is, this is a binary operation and as well as a associative. So you just have to play with the second binary operation, which is dot. That means a dot b equals to b dot a. If this happens, that we call the ring is a commutative ring. Alright, so this commutative ring. Then the last thing today I will just define that the ring with unity. The ring with unity, just I am giving you some definitions. The ring with unity. What is a ring with unity? A ring is called a ring with unity if there exists an element 1. So a ring R plus dot is called a ring with unity. Ring with unity if there exists one ring, one R is denoted as 1r. There exists 1r such that a dot 1r equals to 1r dot a is equals to a. That means if there is an element 1r, but that means it is called a multiplicative identity. That's it. Multiplicative identity. If there exists an element, there is a multiplicative identity, then it called this is a ring with unity. That's it. If there exists a 1r, that means this is called a multiplicative identity. 1r. Okay, 1r. It is denoted by 1r such that a dot 1r is equals to 1r dot a is equals to a. That's it for every a. So it should satisfy for every a inside r, right? Then we call this r is called a ring with unity. So let's just consider some examples, right? Examples. So suppose Z4. What is this? 0, 1, 2, 3. The classes with respect to addition modulo 4 and multiplication modulo 4. Is it, first of all, is it commutative? DIP. Of course it is commutative. You take every two element. Suppose identity will always be, so 1, always you have to check with the multiple the second operation, right? 1 dot 2 suppose, which is actually 2, and 2 dot 1 which equals to 2 by every element. So 3 dot 2, 3 dot 2, the 2 dot 2 equals to, so there is, this is commutative. Yes. Is it a ring with unity? So Z4, so there exists an element in Z4, there exists 1r which is actually 1 such that whatever element you a dot 1 bar, it is to 1 bar dot a which is equals to a for every a inside Z4. Sorry, Z4. So this is called, Z4 is actually, it is called commutative ring with unity. So this is, there exists unity, right? So this is a ring with unity as well as this is commutative. This is called a commutative ring with unity. This is, so Z4 is a CRU, is called commutative ring with unity. This is called a commutative ring with unity. Shortly in it says that this is a CRU. So let it just, what is Z4? Z4 is actually 0, 1, 2, 3, right? And you take a set which is generated by 2. What is this? What is 0, 2 bar, right? So this is a subset of Z bar, and in fact this is a subgroup of Z4. So this is abelian because Z4 is abelian. So in fact this is a subring. In fact this S will form a subring of Z4. S is a subring of Z4. Subring of Z4, right? But my point is it a CRU? It is commutative, okay, but there is no unit. So there is no unit because there is no unit such that there is no 1r inside S such that 1r dot A is equals to 1r, sorry, A dot 1r 1r A dot 1r equals to A for every A inside S. So there is no 1r, right? So there is no 1r, because if you took 0 to be 1r, so okay, there should be a condition, right? No, there is no condition. So A, if you take A to be, suppose 1r to be 2, so 2 into 2 into, suppose 1r, if your 1r is 2 bar, if your 1r equals to 2 bar, right? So then 2 into 2 is equals, is it 2 in Z4? No, because 2 into 2 means 4. This is in Z4, this is 0, so 0 is not equals to 2, so it cannot happen. And 0 is cannot, obviously 0 cannot happen, 0 cannot happen 1r, because if it is multiplied by 0, then it will be by default 0, so it cannot happen. So my point is, S is hovering and of Z4, and Z4 is a CRU, but S has no, S is hovering, being S hovering, S has no unit. So my point is here, the point to be noted is S hovering of a CRU, means commutative ring with unity, may not be CRU. Okay, this point should be noted, that if you asked a question that is subring of a CRU, what can you say about the subring of a CRU? Is it a CRU? No, you will, there are plenty of examples, you don't need to worry about much. So the subring of a CRU may not be subring. This is the example. There is one example. There are more such plenty of examples. You don't need to worry about that. So I think this much is for today, and we'll continue from units and whatever they are remaining units and zero divisors and whatever it will continue from there. And the today's lecture is, I think it is enough for today, and you just have to this is just a definition, and you just have to read whatever book you are comfortable with. You just read the book, and this is just a definition, and you have to verify the examples whatever I have given. You just have since there will not be any need for them, but you definitely have to work with them, otherwise you will not be able to learn anything. So my point is, this is for today, and you just verify the examples whatever I have given for reading, whatever you can check, right? So this is for today, and thank you for watching. This much is for today. Yeah, thanks.